and welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but still want to be its friend. I'm your host, Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and a friend to the universe. We make important phone calls for each other when we can't. I am recording this episode from my office here at Pale Blue Podiversity, and I'm expecting a guest. Caroline D'Angelo is an astronomer turned comedian based in the Netherlands. She took the train all the way to the Podiversity and should be here any minute now. Hello, Caroline. Come on in.
Hi. Thank you. It's great to be here. Thank you. Hey, how are you?
I'm good. How are you doing?
I'm very well. Thank you. I'm exhausted after my train journey. Yeah. Obviously.
Yes. Oh, okay. Well, hopefully we can get you rested after this. But I'm so excited to talk about LIGO and gravitational waves with you. So your rest will have to wait.
Yes, that's absolutely cool. I'm excited to talk to you.
Excellent. Well, I think the first thing I would want to know about you, and the first thing the listeners might want to know, is how did you go from being an astronomer to being a comedian?
Well, I started out as just an astronomer. Well, not just, because I think it's pretty cool, actually, to do a PhD in astronomy. I did my PhD in Germany, actually. So I moved from Canada to Germany in 2006, and I did a PhD there. And then I did a couple of postdocs, first in the Netherlands, in Amsterdam, and then in Leiden. My focus is neutron stars, and especially their magnetic fields. And then after I had my daughter, I decided I didn't want to be an astronomer anymore. So I left. Not
Valid.
Money. I think it's the time, actually. It's not the money, it's the time. I don't mind the money. It's the grant writing and the pressure. So I left astronomy and I moved to data science. So that's actually what I do to earn money when I'm not being a comedian. Nice. But a couple of years ago, I took a stand-up comedy class in the Netherlands with a friend of mine. And there's actually a huge English language stand-up comedy scene in the Netherlands, especially around Amsterdam. There's several hundred comedians kind of doing it as a hobby. There's open mics, there's pro shows, there's kind of everything in between. And it's a really cool, random, weird hobby and interesting scene to be part of. So I've just been kind of doing that for the last 2 years.
That's awesome. Have you noticed any major differences in Dutch humor versus like Canadian humor?
Well, it's interesting because like I perform in English. And so most of the comedians are either English speakers or actually just from all over the place. So that's a really cool thing because everybody is kind of performing. If it's English, then it's usually their second language, but they're coming from Italy or France or, India or something. And so there's this kind of like interesting kind of mixed sense of humor. You see all sorts of different things. The Dutch sense of humor is kind of English speaking comedians complain a lot about it. They complain a lot about like the Dutch people are hard to make laugh, that they're not it's very sarcastic, the Dutch sense of humor. So actually I find it fit in quite well in the Netherlands in general. Right.
I think if you had asked me what I would guess it to be, I would have expected dry, like a very dry sense of humor over there.
Yeah. Like I think the joke is a little bit, when English people are performing for mostly Dutch audiences, they say, people will kind of just stare at you with their arms crossed the whole night and kind of just nod with their very straight faces. And then afterwards they'll come up and say, you were quite funny.
I would die.
Yeah.
I would not know what to do with that.
Like, you just stand in front of an audience, full of silence and staring people. It's like for 45 minutes or something. Well, no, I don't do 45 minutes, but for 8 minutes staring at you. And it's like, yeah, I enjoyed your performance. You could have laughed.
Right.
You could have shown it. Yeah.
Maybe an honest signal every once in a while.
My husband is from Iceland and he says that, people here just laugh in proportion to how funny things are. So he's also kind of a tough crowd. Yeah.
Then you have good practice at home.
Yeah.
Yeah. Okay. I'm especially interested in your answer since you are deeply rooted in astronomy but have since left.
Yeah.
When you think about the universe and how big it is, how do you feel inside?
I've always thought it was amazing. I've always thought it was so incredibly amazing to think, especially when I was an astronomer, thinking about neutron stars all the time. I'm just thinking about these tiny objects that are just unimaginably far. Like we could never get anywhere close to, even the light from them takes thousands of years. Like the light that was produced before the pyramids were built, say. And that's just kind of completely normal for astronomers to be thinking about these things all day and night. And it's just overwhelmingly massive. And these are things that are, by astronomy standards, these are really, really close by, these neutron stars. So it still kind of blows my mind. Like I it's hard to really think about, especially now that I've left astronomy and I don't think about astronomy all the time. Mind-blowing, I guess.
Right.
Awesome, really.
In the literal sense of the word.
Exactly, yeah.
You say you don't think about astronomy much these days. How does it find its way into your life now that you've left?
Yeah, I like keeping up with new discoveries. So what we're talking about today, LIGO, the first gravitational waves were discovered in the last few months before I left the field. And that was just, it was amazing because I always, from the first time I heard about them, it's just the wildest thing, I think. This idea of these like ripples in space and time traveling through it's incredible. And then the fact that they had already been discovered, just been discovered in real life was stunning. So I've sort of kept up with the new discoveries, but I'm sure I've missed all sorts of stuff. So I'm really excited to be talking to you today. And, I keep waiting for someone to really say like, hey, we discovered life on another planet. I'm really excited about the new telescopes, the new space missions that are out and the discoveries that they're making. Euclid, for example, mapping out the universe. Really. So I kind of keep up with the biggest news, but
sounds like it.
I think it's more the way of thinking, right? When you stop being a scientist professionally and you become you keep that scientific way of thinking.
It's a skill set.
Yeah. And I think that's what touches my life most of the time.
I love that because that's something that I try to get across in my science communication work is not necessarily just the scientific information, but the skill set that comes along with being a scientist. And that's something that anyone can cultivate and benefit from.
Absolutely. And I think also there's the sense of wonder. Like I'm really, when I do my job now, and especially since I have kids and I'm so busy, I'm really grateful for the time that I spent doing pure research, just kind of like it was such a privilege to be doing it for so long. Like eventually I decided it wasn't for me and for my life and career, but it's just such an amazing thing to be doing something that's just kind of like pure knowledge seeking and over such an interesting subject. Yeah,
for sure. Couldn't agree more. The next question is a little less serious, potentially. Actually, maybe it won't be for you.
Okay.
Do you feel like your sun sign in the zodiac matches your personality?
Yes. Yeah, it's terrible. I'm the most... I wonder about this a lot. I really worry because I feel like I have to say I'm a very superstitious person. Like I feel like I caused myself to have identical twins.
Like you manifested it.
Like yeah, exactly. I manifested having identical twins. So it's just like, oh, I really want this.
Are you a Gemini? Is this where this is headed?
No, I'm not. No, I'm Scorpio.
Oh, okay.
And it fits perfectly. I'm kind of like prickly and sarcastic, unpleasant generally.
Right. You're going to get your way.
Yeah, definitely. Definitely going to get really upset about it. Yeah. Yeah. So which is not really compatible with the scientific mindset. I think this attitude, but what are you going to do? People are complicated.
Exactly. I think there's nothing more in line with the scientific mindset than being able to hold nuance and complexity at once.
Yes, hold nuance. Exactly.
Awesome.
I do really like pseudoscience and what it teaches us about people and the way that we think and also the way that we find patterns. So, and I think there's a huge long history of people being pseudoscientists also. Like Newton, for example, was an alchemist. Like he discovered gravity during the day and then at night he was trying to make gold with magic potions. And he completely thought this was real.
Get you a man who can do both.
Yeah. I think it's incredibly interesting in real life, just fascinating how people think that energy and kind of the universe manifesting and stuff like that works.
Very cool. Next question. What is one law of physics that you would change if you could? Or one law of nature that you would change if you could?
One law of nature that I would change. Well, I think just kind of make it much easier to travel through time and space. I think this is a real pain in the ass, right? Like we can't go anywhere. We're just so stuck here. Like that would be so great. Yeah, to travel to other planets and actually go meet other aliens and stuff. We'll never meet them. We'll just maybe see that their, oxygen signatures are there. So.
Right.
Yeah.
Right. That's interesting. Are you then also fiddling around with the speed of light through space?
I don't know. I don't typically try to work out how this would work in practice. I think the answer is always like wormholes, right? Like it's just you kind of, it's like Einstein, Podolsky, Rosen paradox kind of. And then you talk for a while and then people are like, oh yeah, sure. That sounds good.
Oh, I like that. Like, don't change anything about the speeds of things, but make wormholes more energetically favorable so we can open them. more easily.
Definitely. I don't know, whatever they did on Sliders. I don't know if you know that. It was a long time ago.
I actually really love Sliders. Jerry O'Connell was one of my first crushes.
It was great. And this is why I studied science. This is that and A Wrinkle in Time was really why when I wanted to study astronomy, well, physics really originally, because it's like, oh, this is so cool. And it's like, actually, maybe you should be writing books about science rather than, studying it.
Yeah. Oh, it's fun to hear people's inspirations like that.
It's really well thought out, 11-year-old me. Yeah.
And final question. Imagine you're an astronaut. We're sending you into space, but we're also giving you control over the playlist. So what song would you like to be playing during blast off?
Oh, my God. I don't know. Something so that I just wouldn't be freaking out. I can't even imagine.
Like Enya?
I think it would I'd be beyond Enya. Like, I'd probably need to be sedated. I don't know, whatever is more relaxing than Enya. So I'm not
just womb sounds.
Yeah, I think something like that. Like, just like, it's going to be okay. Just like, yeah, probably some kind of like ASMR video. I think probably just like some audio track. And then it's just like, it's okay. It's okay. I can't imagine.
That's actually hilarious.
I can't imagine going out into space. That is terrifying. So you
were not one of those astronomers who was interested in getting closer to your subject matter.
I don't go on roller coasters. I can't deal with roller coasters. So yeah, once I found out that like being in outer space was like you were falling all the time, it was like, no, I'm fine. Like, I'm really fine
here.
Yeah. Yeah.
That's so relatable. Okay.
Yeah, it's horrible.
I definitely know you a little bit better now. Thank you.
Yeah. Gives you a pretty good picture. Yeah. Superstitious, stuck on the ground. Yeah. Yeah.
I want to learn a little bit more about your past research.
Absolutely.
Because you mentioned the neutron stars, and I have a couple of updates, like new neutron star things we found.
Oh, fantastic.
But yeah, what did you focus on?
Yeah, so I always thought neutron stars were so amazingly cool. Even from the first time that I heard about them, they just have this incredibly strong magnetic field. They're tiny objects. They distort space and time around them. So the light is traveling in weird ways. It's getting redshifted. It's so strange. And when I was doing my PhD, I was actually studying what are called X-ray pulsars. So those are neutron stars that actually have a companion. So they have another star and they're just ripping material off because they have such a strong gravitational field. They're ripping material off, and it's basically like the material is just falling on the surface of the neutron star like a nuclear bomb going off, like way more energy than a nuclear bomb. And it just shows up as light. And actually, when the neutron star rotates around, it has this incredibly strong magnetic field, and the matter only falls along the pole of the neutron star. So it's kind of like the northern lights on steroids. So you just see these kind of flashes of light as the pole of the neutron star flips around into the Earth's point of view. So you can learn a lot about the magnetic fields of the neutron stars, about the way that matter falls onto them, about also just how fast they can go, because they can get spun up to rotating like hundreds of times a second, these ones called millisecond pulsars. And you can learn all sorts of also about just how matter behaves when it's so incredibly dense. And so I found these very fascinating. I was mostly working on actually the processes, the way that the magnetic field actually interacts with the matter around it. So you get these things called accretion disks. So it's not just the star directly kind of matter directly falling on, but instead there's the sort of disk that forms around the star, just kind of like the rings of Saturn, but it's kind of slowly spiraling onto the star. And my research was really studying the way that the magnetic field would interact with such a disk. And especially when the magnetic field was spinning really, really so fast that almost the material would get flung out. So I was studying processes like that. One thing I discovered was that you could get bursts of accretion. So basically the star would become brighter and less bright. And then I worked with observers to see, could we find evidence that this was actually happening in real life? And we did see that. We saw that in neutron stars, and also there's other kinds of stars that do this, like very young stars also have very strong magnetic fields. You can also see this happening also in white dwarfs. So this was the kind of theoretical, I would make theoretical calculations and then do computer simulations that would show a little bit how the light would change over time. And then kind of gave this to astronomers, or gave this to observational astronomers to look for.
Nice. It's really cool to hear about more the other side of the equation, or the other side of the theory observation fence, because I was very much on the observation side. Yeah. And it's so important for them to work together. No,
definitely. Because you really, it's hard to learn anything. It's incredibly, like this is another thing you asked, how I think of astronomy. It's also just like this kind of like huge open-ended puzzle where you have these kind of building blocks, which are the laws of physics and a little bit what you see, and you're trying to just work out what's happening. Yeah, it's incredibly wild to think that you can do this and actually learn something.
Why I joined. Like, what do you mean we can study galaxies and anything like billions of light years away, and we have moved maybe a few hundred miles away from our planet? Like, that's wild.
Yeah, indeed.
Love it. So I found a couple of stories, some new, what I thought were exciting stories about neutron stars in different ways. And you mentioned how fast these things can spin. You know, I know I have heard about like millisecond pulsars and these things that spin so fast. I thought it'd be fun to tell an example of the opposite. In 2022, so after you left, they found, I say they, it's people using SKA data, the square kilometer array data, and they found a mysteriously long period neutron star of 44 minutes, a period of 44 minutes.
That's incredible.
Yeah. I had never heard of anything that long. I don't know if this is quite the record holder, but it's definitely up there. And it's pulsing in the X-rays. We saw it in Chandra data and also in the radio because they're using the square kilometer array. So they are studying it in multiple wavelengths, and they've seen it get dimmer over the last 6 months. So they discovered it a few years ago, but now it's doing something else, and they don't know really why.
It's really interesting. And does it have another star? So is it like interacting with the star close by?
From what I remember reading, it wasn't in this binary system. It was just like, but I could have missed that.
Okay. Oh, really cool.
Yeah, it's called ASCAP J1832.
Yes.
ASKAP.
They're always very sexy names, these.
Yes, they are. There's a long history of appreciating and mocking acronyms on the pod.
Oh, sure. I can imagine. Yeah. Well, astronomers really work hard at their acronyms, I remember. Yeah.
Really? Yeah. And then the other story was a new method for finding a lot of pulsars at once, especially radio pulsars. Students at NRAO, and I love stories that highlight early career folks. This group of students used archival Green Bank telescope data and combined it with new VLA data, but specifically a VLA survey that was looking at transients. So they combined these two data sets, which span almost the entire sky, and they compared the images in these different wavelengths, and by like taking the difference between the two, they were able to find these transient sources. They found a bunch of new radio pulsars.
Oh, that's really cool. Because remind me, the Green Bank telescope, and what wavelength is that?
It's a radio
It's also
dish.
a radio. Or they're both radio. It's just like different frequencies of radio
Slightly
waves.
different frequencies.
Because like we were talking just now, so the pulsars I usually studied were actually X-ray pulsars, where they're really radiating mostly because there's all of this matter falling off. Yeah, but a lot of pulsars, of course, are radio pulsars, which are just on their own. And then it's really cool that they can turn on and off. Like we think of them just as usually pulsating. That's really neat.
Yeah. I like that we can use old stuff. We have old data lying around that has all of these gems in it, and I like mining data like that. Yeah,
it's definitely a big project. There's a huge amount of astronomical data that people have to figure out what to do with.
Yeah. So when you told me you studied neutron stars, we've already done an episode on neutron stars. So listeners, go check that out. It was really fun to make. But I immediately thought of LIGO and gravitational waves because some of the most exciting gravitational waves we've gathered came from neutron stars.
Oh, yeah.
So I just wanted to do like a kind of rundown of LIGO. But like, I guess LIGO, the advanced LIGO anyway, which I'll get into, I have a timeline of it all, came online after you left the field. But it was around before. So did you hear about it?
Yeah, I think I studied LIGO a little bit when I was as my undergrad, and then it was already an old project. So I can't even, like, I don't even know how long it was in development. It was kind of this pipe dream. Like, it's wild. It is absolutely the most insane instrument you can imagine, because it's measuring distances. I think you have to tell me, like, the size of an atom, right? Like, it's this huge machine.
Yeah, like, they're talking fractions of a proton width.
Like, yeah, they can detect kind of wiggles in the universe that are that incredibly tiny. They had just announced the first black hole merger just a week before I found out I was pregnant, actually. I think
Right.
so. It's very memorable.
What a time.
Yeah.
I was actually going to ask if you remembered where you were when you heard the news of the first
I was drinking. I was drinking in celebration. I didn't know I was pregnant. Yes.
I got it. Yeah. I was TAing a college class, and the professor came in and announced it to the classroom, and we all got very excited.
Yeah. It's incredible. So advanced LIGO.
Yes.
Can you tell how much better? Yeah.
Oh, I'll get to advanced LIGO, which was a huge improvement. But first, I want to go through kind of all of the letters in the acronym and then a timeline for it, because it goes back to the 60s. That's how long it was in development. Yeah. But LIGO, the acronym, stands for the Laser Interferometer Gravitational Wave Observatory. Yeah. I'm going to break each of those down for listeners. Definitely. Laser is also an acronym. Yeah. So it's nested.
It's going to be a long time. Yeah.
Laser stands for light amplification by the stimulated emission of radiation. This basically just means you have a strong, really narrow beam of light, and they were invented in 1960 by a man named Theodore Maiman in California. And when lasers were invented, it kind of set off this cascade of scientific advancement because they're really useful. Light is good at encoding information. So if you can control a really strong beam of light, you're golden. So that's the L in LIGO. The I is an interferometer. Have you thought about interferometers lately?
I have. I think I need to be reminded what an interferometer. What it even is.
I mean, I'm a lot more familiar with radio interferometers. When you have a series of dishes that are all working together to make one big telescope, essentially, because you can combine their data. But we're talking not about light here. We're talking about gravitational waves. So the interferometer looks a little bit different, but the basic idea is the same, where you have a system of detectors that work in tandem. In this case, it's two laser beams that move in opposite directions, and then you combine data from both of the laser beams to make your analysis.
Right, because this is it's like from interference, right? So it's like when you have pond, and then you have these two stones, and they're kind of these interference patterns that you get. And so then you're doing that with light. And so how does that help when you have a laser? How does that allow you to kind of get to gravitational waves?
Yeah. We're going to get to this in the how it works section, but with the laser interferometer, in light interferometers, you basically want as many dishes as possible. That just gives you an advantage. In the laser interferometry, they have these two beams of light, and they are perpendicular to each other. They're at a right angle to each other. And that orientation just gives you data in multiple dimensions for gravitational waves passing through you. If you just had one beam of light, you might miss the stretching and shrinking that gravitational waves make matter do. But if you have both directions of light, you're guaranteed to catch some of the shrinking and stretching.
Okay, because I think we have to go back a little bit and remind me exactly how gravitational waves work.
That's the next one. That's the G.
Oh, fantastic. Good.
So gravitational waves, they've just ignored the W in the acronym.
Yeah, because it didn't work. You're allowed to do that in astronomy.
Yes, you are.
It's a bad acronym.
It's the Wild West out there. It's the Ild Est because they took out the W's.
That's right. That's very nice.
These were first theorized or hypothesized by Einstein in his 1915 general relativity, and it's described all the time as these ripples in the fabric of space-time. So if you imagine the universe as this kind of blanket.
Welcome to the dark side. Welcome
I know.
Through the mirror, through the looking glass, people. What does that mean? Ripples in this fabric of space and time.
That's a great question. I have never been able to find a better way to articulate that myself, because I think it's really hard for people to envision the four-dimensional universe and ripples passing through that. Yeah. But functionally, the way that it actually impacts our material lives is that when a gravitational wave passes through us, the space of our body ripples a little bit. Yeah. So it, in the direction that the wave passes, it gets longer and it gets shorter. It's like something on a pond and a wave passes through and that thing bobs up and down. Yeah. Our bodies bob up and down, but in the direction that the wave moves.
It's wild. So it's like time is passing at a different, because like that's what happens in gravitation or general relativity. When you go very close to a neutron star, for example, time is slowing down compared to a person very far away. It seems to be passing slower. So that's actually happening in your body as these gravitational waves are like, it's happening. Like time is kind of slowing down and speeding up as it passes through you.
Right. I think all of the dimensions are shrinking and stretching. So the time and space.
Yeah. By a lot.
That's by a very tiny fraction. That's why the detector has to be so sensitive to something smaller than the width of a proton, because this, contraction and stretching, it really is that tiny.
It's amazing.
I know. We're so cool that we can discover that we've discovered this.
Yeah, we thought of it and then we actually built something that could detect it. It's wild. Yeah. It's really crazy. Yeah.
And the thing we built to detect it was an observatory. This is the O in LIGO. And it's not like a lot of other observatories that people are probably more familiar with. It's not like a telescope that you can point in different directions. It is fixed in space. There are these two basically like kilometer-long tunnels that run in different directions, and you shoot laser beams of light down each tunnel, and it waits for a gravitational wave to pass through it. So it's much more like the Arecibo Observatory, if people have heard of that, which was a giant dish so big you couldn't steer it, and it just stared up at whatever was above it at the time.
So basically, these lasers that are rippling, they're kind of like a telescope in a way. Because they're actually able to kind of like see or detect things that are happening where exactly, like somewhere in outer space, but like only in one direction. Is that right? Or kind of
basically in any direction.
Okay.
Gravitational waves would pass through the entire Earth, so you don't have to worry about being in a preferred direction or position to see it like you do with light waves, which can't pass through the Earth. So no matter where the gravitational wave originated, if it passes through us, then LIGO can detect it. And it's not the only gravitational wave observatory around the world, which is important. There are 3 others. There's one in Germany called GEO 600. There's one in Italy called Virgo. And then there's CAGRA in Japan, which is another acronym. And by 2030, India expects to have its own gravitational wave observatory.
And so are these all working independently of each other? They
work independently, but they can work in tandem. One of the big discoveries of LIGO was this neutron-star merger. And that was the first multi-messenger discovery where we saw it in gravitational waves. Yeah, and we saw it in light waves. And in order to see it in light waves, you have to actually point a telescope at it. So you have to know precisely where it is. And LIGO's not good at that because it doesn't matter where it is. LIGO's not necessarily set up to triangulate. So I think it was with the one in Italy, with Virgo in Italy, data from that allowed them to triangulate this double neutron star merger so that we could point a telescope and get the light.
Oh, fantastic. And what was it? Because this is a big question in astronomy, these double neutron star mergers. People have studied them.
Oh, like what happened afterwards?
Yeah. Or what happened during the neutron? What did it look like?
Well, what I remember them making a big deal about was the elements that were produced. I remember they saw a lot of heavy elements like gold and silver. I think I remember seeing like a Jupiter's worth of gold was produced. And so it was mostly spectral data that I remember hearing about. But it never occurred to me to actually look up a picture. Let me look it up.
When I was still in academia, that was a big question. So people thought the gamma ray bursts were created by double neutron star mergers. But this is like another cool example of where science can kind of, later scientific developments can answer questions that people had for a long time.
Right.
So
I'm not seeing like an optical image or even like a false color image. So I'm thinking that it was mostly spectral data.
Okay. All right. Cool.
Yeah, we've discovered so many cool things, and that's
definitely.
Hi friends, it's me. Caroline is looking around my office trying to find the densest thing in here, and she is in for quite the treat. But while she's searching, I'm going to share some messages with you. The first is a podcast recommendation this time. The podcast is called This Guy Sucked, and it's a history podcast for haters spy haters. You can join historian Dr. Claire Aubin and a new expert every week to pull back the scholarly curtain on some of the world's biggest bummers. No dead person is safe, and the show's guests prove that the best part of understanding the past is criticizing it. Claire just did an episode on Alexander the Great, so if you like it when I talk about ancient history and weave in a little bit of mythology here on Pale Blue Pod, I think you will love that episode. So check it out. New episodes do come out every Thursday. There's a lot in the catalog already, so search for something that interests you. You can listen wherever you get your podcasts. Next up, I want to thank all of my patrons who support the show financially. I'm an independent podcast, and your support means the whole universe. Thank you so much. I also want to give a special shout out and a huge thank you to my Sun-like stars, Scott Reynolds, Tom T., Nicole Bartlett, and Ashley Shambo. Your gravity is holding down the Pale Blue Pod solar system right now, and I really appreciate you. Thank you so much. You, too, can join this awesome group of people. You can hear your name on the show, make it onto my Patreon star chart, and get research notes for almost every episode for $5 a month at patreon.com/palebluepod. That link is also in the episode description. Or you can make a one-time donation as a supernova at the PayPal link in the description, and that is just as appreciated. Of course, if you can't support the show financially, that's okay. I understand, and you are still space. The best way to help the show grow is actually to get more people listening to it. So take a link to an episode that you love and share it with a person you love. Make listening to Pale Blue Pod a group activity, and more people will befriend the universe. But really, I appreciate any support you can give. Thank you. Okay, Caroline is back. She found the piece of neutron star that I use as a doorstopper when I don't want to be disturbed. The dean of the Nuclear Transfiguration Department gave it to me when I got tenure. She's so sweet. But the kicker is that neutron stars are so dense that the piece is too small to see. It's in this special glass container, and it's really heavy, y'all. So we're going to get back to this episode as soon as Caroline catches her breath from trying to move it. So the timeline, would you like to hear what went into the planning for it?
Yes, definitely. And into all of LIGO.
Into all of LIGO, yeah.
Yeah. How did we get from an idea to... Yeah, definitely.
It started in the 1960s. After lasers were invented, people were like, hey, let's use this for cool stuff. And physicists realized that a network of lasers used together might be good at detecting these gravitational waves that people had heard about or known about for decades, but we'd never been able to prove them. And in 1972, an MIT study found that if you have two laser beams that are at least a kilometer long, then you would be able to detect those gravitational waves. So we figured out how big the detector would have to be.
And why is it so important to have it be so long?
It has to do with the way it works. They are measuring how long it takes the light to travel down each arm at LIGO, and the longer the arm is, the longer it takes to travel, so the greater the difference will be, right? It would just be more noticeable.
Okay. So basically you need it to be a certain length in order to give enough, to be able to measure the time difference that's going to be created by the gravitational wave.
Correct.
Okay.
And also enough space, I think, for the gravitational wave to contract it and stretch it enough.
Oh, cool. Yeah. So you just build a laser that's a kilometer long or longer.
Exactly.
Yeah, exactly.
Yes.
Okay.
And two lasers, so you make sure you never miss the wave.
And I can imagine that also these lasers have to be pretty isolated.
You are correct. I'm gonna wait to get to that because it's cool to talk about.
I'm jumping all over you. I'm very sorry.
It's okay. So that MIT person figures out how big the detector needs to be in 1972, and they get funding along with Caltech in 1979 to try and do some research and development for what a kilometer-long laser could actually look like. They got approved by the National Science Foundation to start getting more serious in their planning, but they weren't funded yet. But that was in 1984. NSF was like, if you did more work on that, we would probably fund it, but you have to have a more concrete plan first. And it wasn't until 1990 that NSF actually funded it with a budget of $300 million, which was the largest NSF grant given up until that point.
Okay, wow. So they really believed in it.
Exactly. And there were, like decadal surveys. There was consensus among the astronomy community that we really wanted to focus on detecting gravitational waves. I think that maybe there had been some embarrassment because for decades we hadn't been able to kind of prove this one huge pillar of Einstein's relativity.
Okay. Interesting. So that was in 1990 that they got this. Mm-hmm. They finally got like money to build it.
Yes. And then they started building it in 1994. That's when construction began at the two sites, which they chose to be Hanford, Washington, so in the northwest, and in Livingston, Louisiana, which is kind of like the southeast of the United States. And they were very careful in choosing those sites. They needed to be a particular distance away from each other, as close to 3,000 kilometers as possible, because that's the distance that gravitational waves can travel in 10 milliseconds.
Okay.
And they wanted it to be like very quick that you get data for both of these observatories.
Okay.
They also needed to be in flat places so that they wouldn't have to level anything. Okay. And they needed to be close enough to civilization that there was good infrastructure for building it and housing the scientists who would work there, but not so close to civilization that there was a lot of seismic noise, because any sort of vibration is going to impact their detection.
So you mean like seismic noise created by people?
Yes. And also by the Earth. It needed to be in like a stable geographic place.
Because I don't think of like people... I mean, yeah, you hear the subway maybe sometimes when you're really close, but you don't think of like our activity as humans making the Earth move. So like what kind of seismic noise are we thinking about?
We do actually with our cars, with our walking. One of the cool things that we discovered when COVID started and people went into lockdown was that we could measure the difference between like human seismic noise and Earth seismic noise. It got so much quieter. And so that's one thing that LIGO is looking out for, because if there's a city or even a small town nearby and people are driving cars, or if there's a coal mine nearby and people are like doing things underground, they need to be far away from that.
That's so great. This is crazy, right? Because these are not big effects. Like how far away does it have? Like kilometers away or?
Yeah, kilometers away.
Yeah.
But they've also done a lot to shield it. So you mentioned before that all of these pieces probably need to be like housed very carefully. Yes, they have one of the world's most advanced vacuum chambers. The whole laser system is in a vacuum.
Like the kilometer. So you have these like kilometer tunnels that are basically a vacuum.
Yes.
And you're just shooting lasers back and forth, trying to detect ripples in the fabric of space and time. This is real. This is real.
Science.
This is science. This is stuff that actually happens. Yeah, that's wild.
I love it.
That's incredible. Yeah, that's so cool.
So back to the timeline. In 1997, the LIGO scientific collaboration was established, and this brought in more people besides just MIT and Caltech. It also included a British and German gravitational wave collaboration. The German side operates that GEO 600 observatory I mentioned. And then in 2002, LIGO and the German Gravitational Wave Observatory, they started working together for the first time. I think just to like kind of calibrate our machine, like see if they can work together, see if their data readouts are especially different. And they got no detections.
Okay.
And so then they planned to do a bunch of improvements, and they knew it would take a long time. The improvements ended up taking 13 years.
Wow.
I know. A lot of that improvement was spent trying to protect the laser and mirror system from vibrations.
Okay.
So they invented a like high-tech suspension system for the mirror that the laser beam reflects off of. And they, I think, worked a lot on this vacuum chamber system. Okay. And they upgraded all of the instruments. So between 2002 and 2015, every piece of LIGO was updated. And then they turned what they called advanced LIGO on in September of 2015 and got their first detection within literal days.
Wow. Yeah. So it's 13 years, but then it worked.
But then it works immediately. And they were like, oh, yeah, we did it.
Incredible.
Yeah. Worth it.
Oh, that's really cool. So when was the first event that they detected?
That was in September of 2015, and then they announced it the following February.
Okay.
They were crunching those numbers for a while.
Yeah.
All right, so I want to talk a bit about how it works in practice. How do they detect the gravitational waves? And it has those two sites. There's one in Louisiana and one in Washington State, that very special 3,000 kilometers apart. And at each site, they do the same thing. And it's important to have two sites so that you can test your data and you can rule out false positives. But both sites are doing the same thing. They have at each site 2 kilometer. Well, actually, I think at some of the sites, they were increased to 4 kilometers long. So they have at each site, they have 2 tunnels that are each 4 kilometers long.
Okay.
And a beam of light gets sent from one source. So they don't send like 2 different beams of light.
Right.
They take one laser and then they send it through what's called like a beam splitter.
Yeah.
And they're doing this because timing needs to be really precise.
Okay.
They wouldn't want to risk sending a beam of light at different times. So it's one beam that gets split and it goes down each arm of LIGO 4 kilometers until it hits a mirror.
Okay.
And when it hits the mirror and bounces back, they are timing precisely how long the laser beam takes to go down and back. And if that value changes at all, and they can rule out other sources of vibration, then they know that a gravitational wave has passed through.
Okay.
They can also kind of rule out false positives because if it is a true gravitational wave, one detector should, go off, and then immediately or exactly 10 milliseconds later, the other detector should go off.
Right.
And if it doesn't, then they know it was just a local vibration.
Okay. And why do you need what is the L shape for again? Because why can't you just measure the time difference? Because you know how long it should take your beam of light to go back and forth one arm, right?
Right. The L shape is to make sure you don't miss any of the ripples. Imagine you drop the pebble in the pond and the ripples go out, but they go out in a circle. Gravitational waves do the same thing. And if the wave is coming at you, by the time it reaches us, it's almost in a flat line, like a wave on the shore of a beach.
Okay.
Imagine the shore of the beach. It's parallel to the wave coming in. It's not stretching or contracting. But if you have another line that is facing, like it's pointing out into the water, the waves are going to contract and stretch that line.
Okay.
So because we don't know where the ripples are coming from and what orientation they'll have when they reach us, getting the 2 arms at the 90-degree angle ensures that we will be able to measure something. Otherwise, we might miss it.
Okay. I think I understand. Yeah. So, because if you were standing at the beach and you have these ripples coming at you, you're not going to see anything. So it's basically you have it in 2 arms so that you catch it somewhere.
Yes.
Okay.
Yes, exactly.
Right. Well, I had another question. Why a vacuum? Why do you need to have it in a vacuum?
I think it's so the light travels in a truly straight line, and so that other particles don't interfere or get on the mirror. Okay. Yeah, you just want it to be a contained system so there's less source of error.
Okay. So it's basically because everything can just mess up your system. Any kind of vibration and any kind of even just air particles can mess up your...
Oh, for sure. Yeah. If you have air moving in that chamber, it can absolutely move that mirror enough. The mirror distance that they can detect, I wrote it down as 1/10,000th of the width of a proton, which is
crazy. That's really crazy. So it's just, this is what I remember from gravitational waves. I think that just every other thing that happens in the world, like air moving or any kind of, I don't know, truck or anything, is just hugely so much larger than the effect that you're trying to detect. That it's just an incredibly small effect. That's very cool.
And that is the only reason it took us so long to detect them. I think we've now had over 90 detections from LIGO alone, and there are more from other observatories around the world. And that shows us that these types of events truly are commonplace. Yeah. Which just confirms a lot about what we know about the universe. Yeah. And there are a few different ways that they can show up on our detectors. The LIGO team has their eyes peeled for 4 different types of gravitational wave signals. The first is a continuous wave. one of the things I like about gravitational wave studies is that the signals are described as sounds, because I think the scientists working on it really want to distinguish it from electromagnetic radiation. They want to make it very clear this is not light.
Yeah.
And so they talk about the signals in terms of like chirps or like buzzing, which is really nice.
Yeah.
So the continuous gravitational waves would create more of like a buzzing sound. And these are produced when you have massive objects that are spinning and dragging space-time along with their rotation, much like neutron stars. They can just drag space-time around them, and that motion is interfering with the fabric of space-time. So it creates these ripples, but they're kind of like low intensity ripples. I don't know if we've found any of these yet, but if we have a sensitive enough detector, we could.
Okay. So this is just like from the spinning of it. Is it neutron stars?
Yeah.
They're expecting
and any other like massive spinning object. So black holes.
And
too.
like kind of stellar mass black holes, like of that sort of size.
Mm-hmm. I think even a larger black hole, like it would just make, higher amplitude. So that's continuous. They also have random waves, like a random signal that could be produced by kind of like the constructive interference of multiple gravitational wave events reaching us at once. Like two stones being dropped in the water and the ripples like build on top of each other in weird patterns as they reach you. We could hear that as stochastic random chirping noises, but we haven't detected that again because it would be like very, very low, even more quiet than the continuous wave.
Oh, interesting. Okay.
And then there's something called the burst wave, where you just get like a really loud, intense signal at once. And we're not totally sure what could cause something like this, but they're on the lookout for it anyway, which I love.
Okay, so this is just they imagine this could happen, and they're looking for it, and then they'll have to find out what's making it.
Exactly.
Amazing. So there could be like new discoveries of objects that we've only ever seen because they have these weird gravitational wave bursts.
Mm-hmm, mm-hmm. And
wild.
That is why just like pure expansive exploratory thinking is so valuable to science, because if we were only looking for signals that we expected or like could understand now, we would miss out on so much, or at least we will once we have stronger instruments.
Okay. Amazing. But what does it mean? Like when you say looking out for, like why isn't it just that you're kind of recording and then you see stuff? What does it mean that you have to look out for stuff? Like,
they get so much data coming through that like they truly could not individually investigate every signal that comes through. So there are pipelines. I don't know how much of it is including artificial intelligence and machine learning these days, but there are computer programs that you can put together to kind of weed out sources that look weird to you. And it would be very easy for someone to program those pipelines to remove a large burst of something if they didn't think it was possible to be produced. But they're not. They're like, this could come up. We don't know why, but we're not going to tell our pipeline to remove it from the catalog.
Yeah, that's also really something interesting to think about, because like we were talking about, like, I think the way that it sounded maybe a little bit earlier is it's just like you have these two detectors and they're just kind of sitting there silently and waiting for two neutron stars to merge, and then you just get this little burst, but that's actually not what it looks like at all, is it?
Right. In reality, it's like chirping and buzzing all the time because there's other sources, and they have to remove the false sources.
Right.
It's also not on all the time. That's another thing. LIGO was on continuously for like a few months, and then they turned it off. And then they turned it on again a couple years later. So it's not like on 24/7.
Okay.
Most of the time, the LIGO team is like running maintenance or analyzing data.
That's very cool. So you just have these like huge amounts of data that you have to look through, and then look through your other detector and look for patterns that you think could be a real gravitational wave.
Right. And then once you see something, you have to go through a bunch of steps to confirm it, see if any of the other observatories around the world also detected a similar signal. It happens slowly.
And then like, how do you even know what you're looking for? Like what pattern, like how do you even know what it's going to look like?
I think that was probably done with a lot of simulation and theoretical work, going back a lot to what Einstein described gravitational waves to be. I would have loved to be in that room when the first chirp came in, and like they were looking for so long. I have to imagine that when they saw it, they knew that was it.
Yeah. Yeah. Right. Because you said they discovered it basically right away.
Right away. Yeah. And it does look different, like, so what we have found, all of these dozens of gravitational wave sources we've found are a very particular type of signal shape. We call them in-spiral waves. These are produced when you have a binary pair. So the first one, continuous waves, that's just a single object spinning. If you have two objects that are orbiting each other, they're spinning around each other, and it's that motion that creates the gravitational waves. But as they're spinning, they're also like getting ever so slightly closer to each other over time. And when they do finally like get close enough that they're moving really fast, that's when the gravitational waves are strong enough for us to detect. So this happens with neutron stars and black holes and other things that are like around that mass whenever they're orbiting each other. This is all of the detections we've ever made.
Okay. Yeah. So it's like two neutron stars. So they have incredibly strong magnetic fields because they're so small and dense. Mm-hmm. And then they're orbiting, and then they merge, and you can see that signal. Mm-hmm. That's very, very cool.
Yeah, and it looks like a chirp, they call it.
Yeah.
Yeah, the sound, like an ambulance coming towards you, goes like, and then it's gone.
Oh, that's very cool.
Yeah, so we've detected at least 90 of these chirps. The first was on September 14th. 2015, and that was two colliding black holes about 1.3 billion light years away. That is how far these gravitational waves travel.
Billion light years away.
Yeah.
So that was like, so when these two black holes merged, what was happening on Earth? Like, it was like, there was like the first bits of life, I think, were happening, and then the signal just traveled through space.
We were still scum in the ocean.
Yeah,
and then...
simple life or something. It was like major extinction events or something. I don't know what happened a billion years ago.
Right. Yeah, but that's putting it explicitly like that is so nice because space is so far apart from everything.
It's really far.
And then I think the next big exciting discovery was that multi-messenger event where the two neutron stars emerged. Yeah. And that happened on August 17th, 2017. So this week is kind of like the 8-year anniversary of that discovery, which is very exciting. And that had to be done in tandem with the Virgo detector in Italy, like I said, so they could triangulate the position of the source. But the chirp itself was fun. It lasted 100 seconds.
Wow.
And that is because these two objects were a lot less massive than the two black holes spiraling in together. So the less mass you have, the longer it takes you to spiral in, and the longer the chirp lasts.
Okay. Cool. And the coolest thing about neutron stars is that they are really mass. So like a black hole is just like a little dot basically in outer space, right? And so they finally just merge and then that's it.
Yeah.
But the neutron stars are actually like, they eventually tear each other apart and collide. And it just is such a messy kind of explosion that we see it on Earth. So that's also a very cool kind of understanding what neutron stars are made of, what matter looks like in that circumstance or in that kind of high density.
Mm-hmm. And I think they have studied the remnant, or they've tried to, but they're not sure if it is a neutron star or a very low mass black hole right now.
Okay. Interesting. But they have detected it.
Yes, they know that it is there. So exciting things are happening with LIGO. They helped us learn that gravitational waves do indeed travel at the speed of light. Again, confirming another part of relativity. But it's in danger right now. Sad part of the episode. The National Science Foundation requests a budget of about $45 million per year to maintain LIGO. And that's what they requested this past year. Actually, I think that was a little bit less than usual. But the current administration wants to slash LIGO's budget to just $29 million. If that is their operating budget for the next year, they would have to completely shut down one of their two sites. And like I said earlier, it's having the two sites that makes it possible, or makes it a lot more reliable to remove false positives. So this budget essentially renders LIGO not completely unusable, but like, what's the point?
What's the point? Yeah. It's a lot of investment, right? It cost a lot of money to build. How much has been put into it so far?
So far, I'd say probably on the order of maybe $500 million has been put into this.
Right.
Which is a lot of money, yes. But in the grand scheme of things, compared to other parts of the United States budget, definitely not too much money to be, adding to our understanding of the universe, in my opinion.
Yeah. But it's also kind of you're taking this investment and you're shutting it down right at the point where you're actually getting all of the rewards for what you put your money into.
Exactly.
So, yeah.
Yeah. And all of those scientists' careers are now in weird, precarious positions. So
yeah,
that is really upsetting. I am glad you're not dealing with that over there.
Yeah.
Very glad.
It's horrible to read about. Really, I have to say, it's a weird time to be reading the news and to be reading what's happening, and also to be following also through Facebook, mostly through other places, that my American former colleagues writing about, writing petitions and suddenly becoming really activist just to keep their careers alive. Really demoralizing to read about.
It is. I saw a bunch of scientists doing like a science fair on Capitol Hill for policymakers, and hats off to them for like coming up with that moment, which has now gotten a lot of attention online. But it really sucks that we are having to fight for science like that. So all of that to say, appreciate the science that we have been able to uncover, appreciate the mysteries we've been able to solve, and engage in curiosity whenever you can, because that's how we fight back against people trying to slash science budgets.
Absolutely. I think curiosity is, it's not just for science, right? Like it's just for life.
Yeah.
All aspects of life. Be curious and search things out. And definitely.
Mm-hmm. But to move on from that sad note, Caroline, what would you want to see from LIGO, a discovery from LIGO?
Well, if I remember correctly, because this was really a while ago, but I think that there's like different sizes of objects can do different things. And at some point I remember, and I don't know if it's LIGO really this is targeted, because I know that there was another mission.
Lisa.
That is also Lisa, right. And that one is in doing the same thing. That's what I wrote a project about. And that's basically doing the same thing, but now in outer space.
In space, yes.
Just for my next trick. But I think I remember reading one of the things that they kind of imagined you could detect with it was the ripples of the early universe. So the beginning of the universe when, there was nothing and then it exploded. And you can see that with the cosmic microwave background, but that's actually from hundreds of thousands of years after the universe formed.
Right.
This initial kind of huge expansion, there's this idea that you could detect that with gravitational waves. So it's basically you'd be hearing the echoes of the Big Bang kind of, I don't know how long, but seconds after it formed, something like that. Mm-hmm. And this underlying kind of stochastic background, this wild to think about. And it would basically, I guess, I'm just talking out of my ass a bit here, but I think it would basically prove that the Big Bang happened, or be added, a new kind of, like you say, this kind of different ways of proving the same thing. That would be an incredible discovery. Already it tells us a lot about the state of matter. I think it tells us a lot about these black holes, things that exist that we didn't even know existed. But yeah, discovering the universe just after it was formed, for me, it's a very kind of, it gives me kind of chills to think about. Mm-hmm. It's a lot of cool stuff. This is what you do when you're in astronomy. You think about this stuff and it's all very just normal for you.
Yeah, I love it. Well, thank you so much for returning to astronomy with me today.
It's been such fun. It's been so much fun. Thank you for having me.
Yay.
It was really, really nice.
Thank you for reaching out. I would love for you to brag about yourself for a little bit. Tell us what you're working on and where people can find you. Share any links you have. Absolutely.
Yeah, well, I am just kind of comedy writing, doing stand-up comedy. I've been doing it, like I said, for 2 years, and it's incredibly fun. It's similar to astronomy in some ways. It's a very creative pursuit. And I love it. I really enjoy it. Just acting in the process of discovery of what's funny and what works with people and what resonates. And definitely when I get up on stage and I tell people I look like a nerd because I have a PhD in theoretical astrophysics. And this gets a lot of applause in the real world. And that's really nice. And I do a joke about neutron stars. And that's also what people remember from me. Mm-hmm. I am on Instagram because you have to be on Instagram if you are in comedy, but I'm not very active on it. But I do definitely have an Instagram. You can follow me at astronomer625 because I chose it when I was going to just creep other people's profiles. And 625 is the square of a square, which is, I think, like me. So I would love to have more followers.
All right.
Like
well,
mostly my mom. Yeah.
Well, listeners, you know what to do then. Check that out. Wait, Caroline, you said you have a neutron star joke.
I do.
Can you?
Well, no, I stand up on stage. One of the first jokes I do, I say, don't worry. I look like a math teacher, but I'm not going to do any science or math jokes. I used to do one about a neutron star, but it was too dense. It gets an undeservedly large laugh. It's one of my most well-known jokes on the circuit.
Oh, that's so good. Thank you for sharing it.
Yeah. My other jokes are of similar caliber. So,
Word. Okay. So you know what to expect, listeners.
But thank you. Yeah, no, it was amazing. It was so cool to be here. And it's really, really nice podcast. Really nice to chat with you. And thank you very much for having me.
Oh, my pleasure. Listeners, I know we spent a long time talking about black holes and neutron stars, the densest objects in the universe. But no matter how dense you are, you're still space. Bye. Pale Blue Pod is hosted by me, Dr. Moiya McTier, a.k.a. the universe's bestie. I created the show with original co-host Corinne Caputo, a comedienne extraordinaire, and help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen, and our audio editing is handled by the incomparable Misha Stanton. I am Go Astro Mo everywhere online, and you can stay in touch with the show and the universe by following Pale Blue Pod on Instagram or checking out our website, palebluepod.com. We are a member of Multitude, an independent podcast collective and production studio. So if you like Pale Blue Pod, you will love the other shows that live at multitude.productions. And if you want a shout out on the show and research notes for every episode, you can join our community over at patreon.com/palebluepod for just about $1 per episode. Thank you so much for listening to Pale Blue Pod. I'll be back next week. Bye.